Question 3. Let's start from simple cases. If n is 1, let's see the animation. It needs one step. And if n is 2, let's see the animation. It needs 3 steps. And if n is 3, let's see the animation. It needs 7 steps. So if we replay the case that n is 3, we can see that the first 3 steps we move 2 disks from needle A to needle B, and the step number 4 we move the largest disk from needle A to needle C, and in the following 3 steps we move the 2 disks from needle B to needle C. So we have an observation that if there are n plus 1 disks, we can move n disks from needle A to needle B first, and then we can move the largest disk from needle A to needle C, and then we move the n disks from needle B to needle C. So we can see that if we can solve the game with n disks, then we know we can solve the game with n plus 1 disks. So let an be the minimum number of required steps for n disks. We have a n plus 1 is 2an plus 1 for this approach. And now we know a1 is 1, a2 is 3, a3 is 7, so we can compute a4 is 31, a5 is 63, and we can guess an is 2 to the power of n minus 1. So let's prove it. So we do induction on n, the number of disks. The best case is n is 1, so a1 is 1 step. It is true. The inductive hypothesis, we assume that an is 2 to the power of n minus 1. And the inductive step, we first want to prove that an plus 1 is smaller than or equal to 2 to the power of n plus 1 minus 1. It means we want to show that we can solve the game in 2 to the power of n plus 1 minus 1 steps. Let's go back to this observation. First, we move n disks from needle A to needle B. So we know that we need an steps. And we can use 1 step move the largest disk from needle A to needle C. And after that we move, it needs 1 step. And after that we move n disks from needle B to needle C. And we can use an steps. As a result, we can solve it in an plus 1 plus an steps, which is 2 to the power of n plus 1 minus 1. Note that we use inductive hypothesis. An is 2 to the power of n minus 1 here. So we have proved that an plus 1 is smaller than or equal to 2 to the power of n plus 1 minus 1. So the next step is we want to prove that an plus 1 is greater than or equal to 2 to the power of n plus 1 minus 1. Which means we want to prove that it needs at least 2 to the power of n plus 1 minus 1 steps. So we can have an observation again that before you move the largest disk, one needle, there must be only the largest disk. And at another needle, there are n disks. And the third needle, it is empty. So it means we need at least an step to move n disks before that. The other observation is after you move the largest disk, one needle, there's only the largest disk. Another needle, there are other n disks. And the third needle, it is empty. It means we need at least an step to move n disks after that. We want to move the n disk to the top of the largest disk. As a result, we know that we need at least an plus 1 plus an step, and which is 2 to the power of n plus 1 minus 1. Again, the inductive hypothesis tells us that an is 2 to the power of n minus 1. So we have proved that an plus 1 is greater than or equal to 2 to the power of n plus 1 minus 1. Since we have proved both equations, we prove that an plus 1 is 2 to the power of n plus 1 minus 1, and the claim is proved. The last thing is, when n is 64, we can compute that 1 century is 100 times 365 times 24 times 60 times 60 seconds. So if there are n is 64 disks, it will need 5 billion and 849 million century to finish the game. So this is question 3.